Hello, welcome to this GCSE Chemistry tutorial on the chemistry of our atmosphere. This tutorial will look at the composition of our current atmosphere, the composition of the Earth's early atmosphere, and how changes over time have led to the production of our current atmosphere. So the first thing you need to know for your GCSE exams is the composition of the current atmosphere. So that's the proportions of different gases in the atmosphere today. So the largest component of our current atmosphere is nitrogen, which is this part of the pie chart, and nitrogen takes up approximately 80% of our atmosphere. The next largest component of our atmosphere is oxygen, and oxygen currently takes up approximately 20% of our atmosphere. Now I know so far we've got up to 100%, but these are approximate figures, so actually nitrogen's around about 78%, oxygen's about 21%, but these round numbers are a little bit easier to remember and they are fine for your GCSE exams. So the next largest component of our atmosphere is argon, which is a noble gas, and argon takes up approximately 1% of our atmosphere. And all of the other gases in our atmosphere are less than 1%, including carbon dioxide, methane, some other noble gases, water vapour, and so on. Now, it might surprise you to see that carbon dioxide takes up less than 1% of our atmosphere, because with all of the discussion at the moment about global warming and greenhouse gases and the problems with putting too much carbon dioxide into our atmosphere, people tend to assume that more than 1% of our atmosphere is carbon dioxide. It's not. Our carbon dioxide is less than 0.05% of our atmosphere, but that's still too much. So the problems of global warming and greenhouse gases and climate change are all still there, even though the carbon dioxide amount in our atmosphere appears to be very, very low from this pie chart. So some key facts from this slide that you need to remember is that our current atmosphere is made up of approximately 80% nitrogen, approximately 21% oxygen, approximately 1% argon. And it also contains traces of other gases, including water vapour, other noble gases, and methane. Now, the rest of the topic of the current atmosphere and the early atmosphere revolves around what the Earth's atmosphere used to be like a very long time ago. So we're going to look at that atmosphere and how it's changed over time. So the Earth's atmosphere has been made up of approximately 80% nitrogen, 20% oxygen and 1% argon for about the past 200 million years, which sounds like a very long time. But the Earth's been around for 4.6 billion years, which is a huge amount of time. And because the Earth began 4.6 billion years ago, we don't have a lot of evidence to be able to identify the gases that were in the early atmosphere. But scientists do have some evidence and they have an idea of what they think the Earth's early atmosphere consisted of. So this is a theory, but this is the theory that you need to know for your GCSE exams. Back when the Earth first formed, the Earth was a very, very hot ball of molten rock. So extremely high temperatures. Now, as the surface of the Earth began to cool, we believe that the Earth was covered in volcanoes, and these provided the gases that formed the early Earth's atmosphere. So volcanoes were producing gases such as carbon dioxide, lots of water vapour, some nitrogen, likely some methane, and probably some ammonia. And these gases formed the early atmosphere, and you need to be aware that there was a lot of carbon dioxide in the Earth's early atmosphere, much more than there is today. Now, we can describe the Earth's early atmosphere as being somewhat like the current atmosphere on Venus or on Mars, and that's important because in your exam, the examiner may ask you about the atmosphere on Venus or on Mars compared to the atmosphere on the Earth. They are not expecting you to know much about the atmosphere of these planets, apart from the fact that it is similar to the Earth's early atmosphere. They're likely to give you some data if they ask you about Venus or Mars, or they may just say that it's very similar to the Earth's early atmosphere. So you need to apply your knowledge of the Earth's early atmosphere to questions that ask about the atmosphere on Venus or on Mars today. So the composition of the Earth's early atmosphere was primarily carbon dioxide, water vapour, nitrogen, methane and ammonia. And over the past 4 billion years, this has changed considerably, and now the composition of our atmosphere looks somewhat different. So next we're going to have a look at some of the changes that happened on the Earth that affected the composition of the atmosphere. I will tell all of this in order, chronological order, and then we'll break it down and look at each gas individually. Okay, so a reminder that when the Earth first formed, it was an extremely hot place. So over time, the Earth has cooled down. Now, as the Earth cooled down, volcanoes formed on the surface. Volcanoes gave out a lot of gases, and one of these gases was water vapour. So we can imagine that as the Earth starts to cool and its surface crusts up, we get volcanoes and we've got some water vapour in the atmosphere, along with carbon dioxide, methane, nitrogen and ammonia. As the Earth's temperature continued to cool, when the water vapour reached a temperature below 100 degrees, the water vapour could cool and condense and turn into liquid water. And that meant that the liquid water in the atmosphere fell to the Earth as rain. So it rained a lot, loads and loads and loads. So much so that it formed the oceans. And this is the first part in our story of how the atmosphere changed from being an awful lot of water vapour to very, very little water vapour. So the key ideas are that the Earth was very hot, the temperature cooled down, the water vapour in the atmosphere condensed, fell to the Earth as rain, and formed our oceans. Okay, so now that we've got oceans, we can start to consider what happened to all of the carbon dioxide that was in the atmosphere. One of the things that happened was that some of the carbon dioxide dissolved into the oceans. And carbon dioxide dissolves better at cooler temperatures, so as the Earth continued to cool down, more and more carbon dioxide dissolved into the oceans. Eventually, we start to see the evolution and the appearance on Earth of photosynthetic life forms like algae. So algae started to form in the oceans. Algae carries out photosynthesis, which means that it can take in carbon dioxide and it can release oxygen. So if you're asked about the removal of carbon dioxide from the atmosphere or how it decreased over time, you need to mention the keyword photosynthesis. You also need to know the equation for photosynthesis. So carbon dioxide is taken in by the algae along with some water, and using the light from the sun, it converts the carbon dioxide and the water into C6H12O6, which is glucose, and releases oxygen gas. So this is the symbol equation, and it is balanced, so you do need to know how to balance equations for chemistry, so make sure that you remember to put those big sixes in as well. The word light above the arrow means that light is a condition of this reaction. It is something needed for this reaction to go. So that's one way that carbon dioxide that was in the atmosphere was removed from the atmosphere. It was taken in by algae and later by plants in photosynthesis. Once algae and later plants started to evolve and produced oxygen, the oxygen in the atmosphere enabled animals to evolve. So we start to see animals such as mollusks appearing in the ocean. These mollusks and other creatures that live in a shell need carbon dioxide to form the compound that makes the shell. So carbon dioxide that has been dissolved into the oceans can be taken in by creatures that have shells and can be turned into carbonate ions, which can form the seashell. So another way that carbon dioxide was removed from the atmosphere, apart from being dissolved into oceans, absorbed by algae and plants for photosynthesis, it also was absorbed or locked up in seashells as carbonate. Now over time, these seashells die and they fall to the bottom of the ocean, and we end up with a build-up of seashells at the bottom of the ocean. Over time, the pressure on top of these and the sediment on top of these causes them to squash together and they become sedimentary rocks, such as limestone. So the carbon dioxide that was in the atmosphere, that dissolved into the oceans, that went into the shell to make the carbonate material to produce a shell, ends up locked up in sedimentary rock, such as limestone as well. So some of it has been used for photosynthesis, some of it has dissolved into the ocean and is still in the ocean, and some of it gets locked up in sedimentary rock. Now, as you should know, dead sea creatures on the sea floor, under immense pressure for a long time, can turn into fossil fuels, such as oil and natural gas. So some of the carbon dioxide that was in the Earth's early atmosphere was also eventually locked up in fossil fuels. Okay, so for a quick summary for each of the gases that have changed considerably in our atmosphere, we will start with water vapour. So there was lots of water vapour in our atmosphere, which was released from volcanoes. The Earth's surface was extremely hot. As the Earth began to cool, water vapour was able to condense. So the water vapour in the air began to condense and fall as rain. This was an awful lot of rain and formed the Earth's oceans. So overall, the amount of water vapour in our atmosphere has decreased. So next we'll look at carbon dioxide, and carbon dioxide is the most complicated one because there are lots of things that have affected the amount of carbon dioxide in our atmosphere over time. So first of all, we've now got oceans. So the carbon dioxide dissolved into the oceans, and more of it dissolved as time went on because the Earth was getting cooler and carbon dioxide is more soluble at low temperatures. So some carbon dioxide dissolved into the oceans. Some carbon dioxide in the oceans was absorbed by photosynthetic organisms such as algae who were doing photosynthesis. You need to know the equation for photosynthesis in words and a balanced symbol equation, but the algae absorbed the carbon dioxide and produced oxygen, taking away more carbon dioxide from the atmosphere. On land, plants evolved eventually, and these plants, they also absorbed some carbon dioxide from the atmosphere for photosynthesis, converting it into oxygen, which is another gas that we'll look at separately. Once we had enough oxygen in the atmosphere, animals could evolve, so we had animals such as sea creatures, mollusks, and so on. These sea creatures, which have shells, absorb carbon dioxide to turn into carbonates to make the shells. So some carbon dioxide was locked up in carbonate shells of sea creatures. When these sea creatures died and fell to the bottom of the ocean, they all stacked up, and after many years of pressure and a very long time, they got squashed into sedimentary rock, such as limestone. So some carbon dioxide was locked up in sedimentary rocks. Now, because these sea creatures have fallen to the bottom of the ocean and they are being put under immense pressure, some sea creatures at the bottom of the ocean went on to become fossil fuels such as coal, oil, and natural gas. So the fossil fuels, coal, oil, and natural gas, were formed from sea creatures which had shells. Some of them became sedimentary rocks, some of them became fossil fuels, and because they had shells, they had previously taken in some carbon dioxide from the atmosphere. So some carbon dioxide from the atmosphere ends up locked up in fossil fuels. That is another place that you need to remember the carbon dioxide has gone. So overall, from 4.6 billion years ago to our current atmosphere, the amount of carbon dioxide in our atmosphere has decreased due to all of those different processes. So the third gas is oxygen that we need to consider. Oxygen in the early atmosphere was non-existent. There was little to no oxygen in the Earth's early atmosphere. Oxygen only came about because early life forms, such as algae, converted carbon dioxide in our atmosphere to oxygen, releasing oxygen into the atmosphere. A little later on, after they had started to evolve, plants also absorbed carbon dioxide and released oxygen gas through photosynthesis. Again, you need to make sure that you know the equation for photosynthesis, carbon dioxide plus water, making glucose and oxygen. But this is where the oxygen came from algae and plants carrying out photosynthesis. So overall, from the Earth's early atmosphere to now, the amount of oxygen in our atmosphere has increased. And it was this increase in oxygen over time that eventually allowed animals to form, beginning with very simple animals in the oceans and eventually leading to animals such as ourselves. So they are the main changes in the early atmosphere to the current atmosphere. So we have got lots and lots of carbon dioxide in the early atmosphere, reducing over time through photosynthesis, carbon dioxide dissolving in oceans and being locked up in seashells, sedimentary rock and fossil fuels, leading to carbon dioxide existing in just trace amounts in our current atmosphere. Likewise, we've gone from absolutely tons of water vapour in the Earth's early atmosphere down to trace amounts now, and this is due to the cooling of the Earth and the water vapour in the atmosphere condensing, raining and forming oceans. And the third gas, oxygen, we had none in the early atmosphere, but due to plants photosynthesising, over time the amount of oxygen started to grow in the atmosphere, and now we're at 21%. So that's it for the composition of our current atmosphere, the composition of our early atmosphere, and the main changes to carbon dioxide, oxygen and water vapour that have led to the composition of our current atmosphere today.